Okay, this numerical example, which is P14.1, is taken from the R.C. Hibbeler book. So in this case, you need to determine the work of the forces when it displaces 2 meter. And this is one of the numerical example in your tutorial sheet. And in this example is consisting of from A to G parts. So you have to find out the work done for all these cases. So in the first case, what do you have? You have a force which is applied to the block here, and the block is moving through a distance of 2 meter, and the direction of the force is you can calculate from this small triangle here. Okay, so in the first case, in part A, okay, in the part A, you can calculate the work done by this force P, which is equal to tangential force, or you can say it's P cos theta into 2. Okay, so in this case, the angle can be this angle here. So this means that P cos theta is the force which is in the direction of the displacement, and you can split this force into two components. One is going to be this force, which is F cos theta and P cos theta, and one will be this force, which will be F sin theta. So the force which is this force here, this is F cos theta, which is in the direction of the displacement. So you will calculate the force in the direction of the displacement, and then you will multiply this with the displacement to calculate the work. So in this case, you are given the P, which is 500, and the cos of the angle can be calculated from this small triangle. So cos of the angle is 3 divided by 5. So into 2. So from here you can calculate the work done, which would be 600 joule, which is Newton meter. Now in the case B now, so in the case B, if you see the displacement is in this direction and the force is in this direction, so all the force is in the vertical direction and the displacement is in the horizontal direction. So this means that this force is doing no work because there is no displacement in the direction of this force. So in this case, simply you can write that in part B here, in part B, the u of the force will be equal to 0 because there is no work done by this this force here, and some other force is moving the is the body here, but we are not interested in that force. We are only interested in this force, and from here we can see that this force is doing no work. It is just pushing the body against the wall, and there is no displacement in the direction of the force. So therefore the work done due to this force is 0. Now in the case C, okay, in case C, because the force is variable, so therefore we will have to do the proper integration here, and we will have to go back to the initial definition of the work, which is u of this force will be equal to from 0 to 2. So the distance here is from 0 to 2 here, and then the ft ds. So if you just put the value of the ft, which is the force here is in the direction of the displacement, so this means that the whole force is obviously equal to ft. So this is 0 to t, and then ft is 6s square ds. So you can take s out of the integration, so that will become 0 to 2 s square ds. So then it will become s cubed by 3. The integration of s square is s cubed by 3, and 0 to 2. So if you put the limits of the integration, so it will become 6 by 3 and 8 square minus 0. So this means that UF will become equal to 16 Newton meter, which is 16 joule. Okay, now we can go to case D here. So as you can see in case D, the force is in the vertical downward direction, but not the body is now on some inclined plane, and it's not in the horizontal direction. So the plane is now some incline, and again the body is moving along the plane at a distance of 2 meter. So now in this case again, you can use the same equation that UF should be equal to, which is the work done by this force. So either you calculate displacement in the direction of the force, or you calculate a force in the direction of the displacement. So in this case, as you can see this, you can say that it is F T into ds, and S1 to S2, which is obviously Ft into S in this case. So Ft, if you want to calculate, we will need to calculate the tangential force, so which is this force here in the direction of the displacement, and another component of the force will be in this direction here. So we know that this component, which is the normal force Fn, is doing no work. The only work is done by this Ft. So if you can see this, this angle here is, if this angle is theta angle, if this angle is theta, so then so here you can see that this one is parallel to this one here, and in this case so if you draw this triangle like this one, so in this case you can see that if this is our angle theta, so this line, which is the vertical line, is perpendicular to this line here, and this one is perpendicular to this line here. So this means that this angle is also theta. So if this angle is theta, so this means that this angle is also theta. This is our angle theta here. So if this is angle theta, so then we can calculate the UF here, which will become Ft. So Ft will become 100, and sine up theta into S, which is 2. And now this sine of theta in this case is 3 by 5 into 2. So from here you can calculate the value of the work, which is 120 Newton meter, or 120 joules. So this was part D. Now we can solve this part E here. Now in part E, again a force is applied at some angle here, and the block is moving in the horizontal direction. But now F is not constant. F is changing according to this this plot here. So you can see that from 0 to 1 it's changing this way here, and then from 1 to 2 it's changing according to this this equation here. So in this case, because the force is not constant, so we cannot use the just simple the constant force formula. So we will need to go back to this to the basic formula for the work, which is UF, which is work done by force F, is equal to S1 to S2, and the tangential force times ds here. So we will have to do this this proper integration here. So now in this case, if you see here, again from 0 to 1, the force is changing this way, and then from 1 to 2 the force is constant, which is 20. So this means that we can split this integration into two parts. So from 0 to 1 we will have ft1 ds, and then we will have from 1 to 2, then it's constant, so we will have ft2 ds. So now we need to calculate equations for the ft1 and ft2 in term of s here. So if you want to calculate the equation for the first part, which is from 0 to 1 for the s, so if you consider this this triangle here, so this was our f and this is our s, and we know that the distance, the force is changing with the distance according to this equation here, and we know that this is 20 and this is 1. So from 0 to 1, this is how the force is changing with the distance. So now we want to find out the equation of this force. So if we consider this, this is our f and this is our s here. So we want to and we can take this as our angle theta. So we can say that here that tangent theta equal to tangent theta, and from here then we can calculate this. We have two triangles here. One is this small triangle, one is this big triangle here. So for the small triangle we can write that f divided by s, and for the big triangle this distance is obviously is 20, and from here to here is 1, so it will be 20 divided by 1. So from here we can get the equation of the f this ft or f which is 20s. So we derive the equation between f and s for this first part from 0 to 1. So this is our f1, and f2 is just constant, so it will be just 20. Okay, so now we can put these equation back in this equation here. But again, if you see this f, so f is changing, the magnitude is not in the tangential direction to 2. So first we will need to calculate the tangent force here. So then the uf will become 0 to 1, and 20s is the total force, but we need to calculate ft. So ft will become cos of this force. So this is our angle theta. So 20s cos theta into ds, and then plus from 1 to 2, and then f2 is our 20, and again ds. Okay, so here you can simplify this equation. So it will become 20, and cos theta here is just 4 by 5, and this is 0 to 1 s ds, and this will become 20, and 1 to 2 1 ds. So it's just a very simple integration. If you do the integration, what you will get, you will get 24 j here. So this is how you will solve the this part here. Now for the part f here, which is the one with the spring. So for the first part here, for the part f, spring is originally compressed 3 meter. So as this is a spring attached to a mass here, and the stiffness of the spring is given, which is 10 Newton per meter, and originally the spring is compressed 3 meter, and you move it through a distance x. Now for the spring, we know that the work done by a force, which is ufs, the work done by the spring force. We know the equation which we derived in the theory, which is minus half k x2 square minus x1 square here. So now in case of this spring here, what you will have, you will just need to k here is given, which is 10, and x2 here is given. So x2 is when the spring was moved by 2 meter. But as you can see here, the spring is originally compressed 3 meter. So this means that at this location, the x was 3, and then at this location, when you open the spring 3 meter, 2 meter more, so then this means that the compression in the spring will be 1 meter. So this means that x1 is 3 and x2 is 1. So then you just need to put these values here. So x2 in our case is 1 square, and x1 is 3 square. So this is important to notice this thing here, that the spring is originally compressed at 3 meter. So at this location, the spring was compressed 3 meter here. So this means that the spring was already in compression, and then you open it 2 meter. So this means that the spring at this position is still compressed 1 meter. And here you have x2 minus x1, so the final position minus the initial position. And then from this equation, you can calculate the value, so which will become 40 plus 40j. Okay, and finally we can then solve this part G. So as you can see in this case, now the body is moving in this direction, but the applied force is in this direction here. So this means that some other force is moving the body, but we are not interested to calculate the work done by that force, but we are interested to calculate the work done by this 100 Newton force when the body moves in this direction here and the force is applied in this direction. So in this case, obviously we know that F UF, which is the work done by this force, is equal to Ft into S, which is the tangential force time the S, the displacement. And in this case, we can see that the tangential force is in the opposite direction to the displacement, which is 100 cos of angle theta, and angle theta can be this angle here, and S here is 2. So if you, but again you need to put a negative sign here, because the force and displacements are in the opposite directions. So you can say that minus 100 and 4 by 5 into 2. So from here you will get minus 160 joule, and this is negative because the force and displacements are in the opposite direction. So this means that you are working against the force.